So, hello everybody, good morning. It's my pleasure to welcome here again Sudipta Hensh, Dr. Sudipta Hensh, our previous doctoral student, now a full doctor. He's now here in Opava still, but he's going to start his career or his next career in Osaka University in Japan. And probably you have participated at the previous seminars concerning kinematics of spacetimes and tidal heating, etc., etc. And he's going to continue now, to present the part 3, evolution of null congruences. That is, as you can see, the third seminar from the series of seminars of total 6 seminars. So I can ask him to start. Again, welcome here. And if you have any questions, we can discuss once the seminar is over. So welcome, Sudipta, and you can start. Thank you.
Yeah, thank you. Thanks everyone for being here. Yeah, so today we'll discuss about the evolutions of non-congruences in the context of a space-time that includes torsion. And this work was done in collaboration with Professor Stefano Liberati from CISA. Yeah, so here is the content of today's seminar. First, I will spend some time on quick recapitulation of previous lectures, and then we'll discuss about the projection operators and decomposition for non-congruences, and then we'll slowly get into the equations for non-congruences concerning expansion, shear, and vorticity of the congruences. These equations are called Raychaudhuri equations, and we know that they have quite big impact in studying many things, which is also the basis of Penrose's singularity theorem. So these are the definitions. I will go very quickly in these slides, just to remind ourselves from what we did in previous lectures. Yeah, so the covariant derivative for a generic 4-vector x beta can be defined as this, nabla alpha x beta, where C is the generic connections, and that can be written as Lebesgue plus some antisymmetric part, and that antisymmetric part is basically contortion, which is a tensor that can be formed due to the presence of torsion. And here we are assuming 0 non-metricity. That means the covariant derivative of the metric is 0 always. And torsion is defined as the antisymmetric part of the generic connections. Here you can see S alpha beta gamma is the antisymmetric part of the generic connection. And also, it's by definition, we can see that the torsion tensor is antisymmetric one. So it is antisymmetric in its first 2 indices. And as I said earlier, so generic connection can be written as Lebesgue plus some tensor, which is contortion tensor, and contortion tensor is the combination, can be written as the as some combinations of torsion tensor, as you can see here. So Lie derivative of a vector v along another vector u takes the form this, and if we just replace the partial derivative with covariant derivative, then we see a term appears here, and that is completely due to the presence of torsion. And also we can see the definitions of Riemann tensor with respect to a generic connection can be written as this. This is the standard definition of Riemann tensor.
Sudipta, sorry for interrupting you. Can you expand the full screen? Probably it can be better for us. I'm not sure whether it is your intention to have this to see all the parts, or
you mean the full screen? Can
just
yeah, it is full screen. I think it is because of the ratio. It is like that.
oh, okay, so that's fine. Just
yeah, but you see the material, right?
Yes, we can see everything, but we
okay.
can see also the file, edit, view, go, bookmarks, and etc. So
is it so? Okay.
Yes.
Yeah, I think you can just do view full screen. Yeah, because we can see all the options up. So you just Control F or Control L.
Okay. So maybe I'll share
again. No, that's you.
Yeah. So then view
full screen. Oh, cool.
Okay.
Okay. No, I don't know what are you using there, man.
Or fit page. Or
yeah.
fit.
Now you see. Yeah. Now also you see now the files and all that.
Yeah.
Yes.
Okay. So I'm sorry. Probably it's because of this stupid ocular. Yeah. Yeah, but you see the content, right?
Yes, we see. Okay, so continue. Sorry for interrupting.
Maybe we can continue. Okay, so yeah, so the commutator of covariant derivative, it is also different than the torsionless case. We see here a term appears due to the presence of torsion, and the generalized Ricci tensor can be written as this. Just the one indices contracted, and the Ricci square, it can be defined as this Ricci tensor contracted with the metric. So how the evolution of separation vector propagates along the space-time, this to understand this, we need to define the separation vector, which is xi alpha, and that is just the partial derivative with respect partial derivative of that the tangent vector with respect to partial derivative of the flow vector with respect to the indices s, and also we can define the tangent vector like this, u alpha, and this we need because when a bunch of curves propagates on the space-time, then we what is the most important thing is that the separation between the adjacent curves, and the separation between the adjacent curves, how it propagates along the space-time, that basically determines how the bunch of curves propagates in the space-time. And we also proved last time that this Lie derivative of the tangent vector along the separation vector and vice versa, they are trivially null. And using that, we can also define that this Lie derivative of tangent vector along the separation vector can be written as this b beta alpha xi beta, where b is this. So this b is basically responsible for the propagation of the, how the bunch of curves propagates in the space-time. So we need to calculate b, and when we have b, then we basically can calculate everything. So we here we have shown that this perpendicular component of b is the tensor responsible, or the component responsible for the propagation of the how the evolution propagates along the direction of flow, that basically determined by this perpendicular component of b. And here is the pictorial representation of the congruence evolution. And as you can see here on the extreme left, that is shown the expansion of the congruence, and in the middle we can have, there can be shear, and also we can have twist, which is shown at the right. So in order to decompose the tensor B alpha beta, we need to define a projection operator that basically projects the B tensor on the hypersurface orthogonal to the direction of flow. So in order to do that, we can define H alpha beta as G alpha beta minus sigma U alpha U beta, where sigma can be -1 or +1 depending upon the properties of the congruences, whether it is time-like or space-like. And we can decompose B as a perpendicular component or parallel component. Perpendicular and parallel, that is basic with respect to the direction of flow. So we can decompose B with the help of projection operator, and we can write this component as this, as you can see here, expressions with respect to I mean using H and B. And the tensor B can be decomposed as expansion plus shear plus twist or vorticity. So the expansion expression is just the trace of a perpendicular component of B, and here is the shear. Shear is traced out symmetric part of this perpendicular component of B, and vorticity is just the pure antisymmetric part of perpendicular component of B. So projection operator for time-like congruences, we can write this as G alpha beta plus V alpha V beta, where we can see that this projection operator is perpendicular to the direction of flow. If we contract with if we contract with the tangent vector, then we see that this is 0, and also we see that the trace of this projection operator is the dimension number -1. So here we see that this perpendicular component of B can be written as this. I mean, with the expression, and to derive it, it will take some time, but I think we did last time. But just for completeness, we can see these expressions, and here we have only used the metric compatibility, where what is basically zero non-metricity, and also the symmetric, the contraction of, sorry. Yes, and also the contraction of symmetric and antisymmetric tensor, which is basically 0. So in order to calculate the evolution equations for expansion of time-like congruences, we can just write the expression without torsion as this, and then we can just prove that the theta, that is expansion, with torsion and without torsion, they are basically just the same. So using the antisymmetric properties of the contortion and torsion, we can get theta and theta tilde, theta equal to theta tilde. So here we can calculate, I mean, we can follow the steps here, and eventually we get theta equal to theta tilde, where theta tilde is the expansion with respect to Levi-Civita connection, and theta is the full theta is the expansion with respect to full generic connection. So if we proceed further, then we can see that the Raychaudhuri equation for theta and theta tilde, they are basically the same. So that means that the Raychaudhuri equations is formally same even without torsion and also with torsion. So we can just replace this. This is the expansion. This is the expression for Raychaudhuri equation without torsion, where tilde quantities are calculated with respect to the Levi-Civita connection. So we have here expansion square, and this is also the shear square and vorticity. Yes, quadratic term with the vorticity one. So you can here write the expression for shear, and expression for shear can be written as this, and then we can expand the full shear equation as this. And if we expand this and just try to modify it somehow and put the other torsion related term in F alpha beta, then we see that sigma alpha beta, which is the shear with respect to full connection, that means with torsion, is equal to shear without torsion plus some contribution due to torsion, which is hidden in F, and F is written here. And if we proceed further, and we can see here the Raychaudhuri equation governing shear on the left hand side, and here on the right hand side we have the this d tilde sigma tilde alpha beta d tau is the Raychaudhuri equation without torsion plus some corrections due to the presence of torsion. So if there is no torsion, then all these terms except the first one on the right hand side will be zero. So we will recover the Raychaudhuri equation without torsion. And if we just substitute the Raychaudhuri equation for shear without torsion in previous equation, then we get these equations. Just for completeness, it's I understand that is quite big equation to follow. And this is the expression for vorticity without torsion. And if we just write the just follow the same trick as earlier, that omega is the vorticity and omega tilde is the vorticity without torsion plus some contribution due to torsion. And if we follow the similar treatment, then we get that the Raychaudhuri equation for vorticity in a torsion full case is equal to the Raychaudhuri equation for vorticity without torsion plus some contribution that arises due to the presence of torsion. And if we substitute the Raychaudhuri equation without torsion, then we get just this equation. So that was the time lag case which we did in previous, which we discussed in previous seminars. So now we will discuss about the null cases. And null cases is a little bit different than the time lag cases. So I will mainly discuss where there is differences, because the treatment is more or less similar. So only difference is that how to define projection operator for null congruences. If we remember that we defined the projection operator for time lag congruences as G alpha beta plus the V alpha V beta, but we cannot do this here because the properties of null congruences is a bit different. So in order to define a projection operator for null congruences, we need the help of an auxiliary null vector, this epsilon alpha, such that this k alpha epsilon alpha is equal to -1, and epsilon alpha is also as you said, it's a null vector field, so it is 0. The normalization is 0 here. But and this k alpha is the tangent to a null congruences. So we need the help of another auxiliary null vector field epsilon alpha in order to define the projection operator for null congruences. And here it is -1, but we can write here minus anything. We can just scale this epsilon vector accordingly. We will always have minus. We can always scale this epsilon alpha and get the -1 on the right hand side. So the projection operator is defined for null congruences as this H alpha beta is G alpha beta plus K alpha epsilon beta plus epsilon alpha K beta. So earlier we had this G alpha beta plus K alpha K beta or V alpha V beta for time lag cases, but we cannot do it here because we have different properties due to the null congruences. And if we just check whether this projection operator is perpendicular to the direction of flow, then we see here it is perpendicular to the direction of flow. Also, it is perpendicular to the direction of auxiliary null vector field. So if we just check H alpha beta K alpha, then here it will be K beta, and here it will be 0 because K alpha will be 0, and here we will have epsilon alpha K alpha is -1, so here K beta minus K beta, so it will be 0. And yeah, so this is the trivial H alpha beta equation expression. And here sorry, here's a mistake, so it should be sigma. So H sigma sigma or trace of H should be n-2. So earlier we had n-1, and as we know that this hypersurface orthogonal to null congruences is if the dimension is n, then that should be n-2 dimension. So we have here n-2, and we are also considering that the photon follows geodesic determined by the Levi-Civita symbol or Christophe symbol or Levi-Civita connection. So we have here K alpha nabla tilde alpha K beta equal to 0. So we are not assuming that even in torsion full cases the photon will follow the geodesics, because then there will be some extra effect due to the torsion, and it cannot be guaranteed that if it is following the geodesic with respect to Levi-Civita connection, it will also follow with some generic connection. It is not the case. And if we now calculate the projection of B alpha beta onto hypersurface orthogonal, then we see here how this expression for B perpendicular alpha beta gets modified for null cases with respect to the time lag cases. So here is the expression for perpendicular component of alpha beta, and if we just use the expression of projection operator, and if we expand it, then we'll eventually get these equations. So maybe we do not need to get the details of this, but we can see that here it is yeah, there are many more terms that arises due to the presence of torsion. So without torsion, or most of these terms will go away. And also here we can see that without the presence of torsion, if we just turn off the torsion, then we see the expression for B perpendicular alpha beta as this. So the next task is the expansion scalar for the null congruences and how to define it. Then we, as we know that the expansion scalar is just the trace of B perpendicular alpha beta. So if we just take this trace, then here we see that the other three terms, they are just 0. So we have this expression. And if we follow the similar trick, then we can prove that this theta equal to theta tilde all is true also for null congruences, which was the case for time-like congruences, but it is also true for null congruences. So here we have, for example, here we have, for this term, we have used the properties of summation of, or combination of, or sorry, contraction of symmetric and antisymmetric tensor. So S is antisymmetric by definition in first two indices, and here we have K gamma, K alpha. So we see here this is 0. So, and K gamma, K alpha, it is symmetric and it is antisymmetric. So if we contract it, there will be 0. And here this one, we can see that epsilon gamma, nabla gamma, K alpha, this is just the geodesic equation, or as you say that the photon follows the geodesic for okay, no, sorry, it is because K alpha is a null, is tangent to a null vector. So if we just calculate this, because K alpha is 0, so this will be will also be 0. And here we have used some normalization constant, normalization relations, like K alpha epsilon alpha is -1, like that. So eventually we will get theta equal to theta tilde also for null congruences. And if we follow the very similar trick like we did for earlier time-like cases, so it is, at least formally, it seems that the Raychaudhuri equation for expansion in the case of null congruences is same for torsion, for the case of torsion and without torsion. But here is some difference. We can see here that this expansion scalar, this is shear, quadratic term of due to the shear, and quadratic term due to vorticity. They are there, but also we have here Ricci tensor, and the Ricci tensor is not same when we have torsion and when we do not have torsion. So when we have torsion, this Ricci tensor will get modified, and we will have different expression for, or different weightage for Ricci tensor when we have torsion. So these expressions are looking at least formally same, but they are not quantitatively same when we have torsion. And this we will discuss more detail when we will discuss in the next lecture how the singularity could be avoided in the presence of torsion in a gravitational collapse and all that. Then basically we will have we will quite clearly see how torsion affects the form of this Ricci tensor and modify the Raychaudhuri equations for null congruences. And here, yeah, so we have the expression for Raychaudhuri equation for shear. Is it just the expression, because the trick is very similar that we have discussed for time-like cases. So we have here in square bracket the Raychaudhuri equations for shear due to the propagation of null congruences for torsion-less cases when there is no torsion, and the corrections are here due to the presence of torsion. And here H alpha beta is written, it's quite a big expressions. So the trick to derive the shear equation also for null congruences, they are very similar, but we have more terms for null congruences. It's not more, but quite a lot. for null cases. Null cases are always a little bit complicated. And here we have the expression for Raychaudhuri equation due to the propagation of null congruences and for vorticity. So we see here in square bracket the Raychaudhuri equation for vorticity due to null congruences, and the other terms that arises here due to the presence of torsion. And here we see the differences that we have here n-2 because as we agreed earlier that n-2 is the dimension of the hypersurfaces for null congruences. And here W alpha beta is given below. And also the difference with respect to the time lag cases is that here we have much more terms due to the null congruences and the complexity of defining the projection operator and all that, because we also have some auxiliary null vector field which also arises here in the equations. So the summary is that we have managed to generalize the Raychaudhuri equation for the space-time with torsion, and these equations do not assume any theory a priori and is purely geometrical, and we can just use these equations for any theory of gravity. And this theory of gravity mainly hidden inside the Ricci tensor, so we can use any theory and we can get the expression for Ricci tensor. Because of that theory, we can use these generic equations, or this in more correct way use these geometrical equations. And as you see that we have managed to write it as Raychaudhuri equation with torsion equal to Raychaudhuri equation without torsion plus terms that arises due to the presence of torsion. And the main difference for the non-congruence is that we have more terms due to the presence of torsion, and this is simply because the null cases is more complicated, and we have to define here an auxiliary null vector field in order to define the projection operator. And this okay, so one point to mention, the definitions of this projection operator is just a definition, or is just a machinery to derive the equation, and it doesn't have any role in modifying the equations also. Why I'm telling this? Because one might see that, or one might think that this definitions of auxiliary null vector field could influence the equations, but it will not influence the form of the equations, because we can always rescale or we can always write the normalization equation in such a way that we will always have the -1, as I said, on the right hand side, and the auxiliary null vector field will get modified, but the overall equations of will formally always be same. So here in the case of null congruences, we have more or less very similar equations like earlier, but we have a little bit complicated equations. And the main difference, as I already mentioned quite a few times, that the definitions of projection operator, and also if we think about the importance of this equation, then definitely the expansion equations for null congruences is quite important, and also historically important, let's say, because these equations is the basis of Penrose's singularity theorem, and one can use this equation to study gravitational collapse and all that. just the expansion equations, but also the set of equations, the expansion, shear, and vorticity, they are coupled equations if you already have seen it. So if there is any perturbations on the horizons of a black hole, and we can intuitively see that this excitation could be released by the emission of gravitational waves and all that. So in this case, we can just evolve the system of equations and see how the shear and vorticity is relaxing over time. But it needs much more numerical approaches, because they are coupled differential equations and quite hard to solve analytically. So yeah, there are references that I have used. So if you are interested, you can follow these references, or you can ask me anytime. And thanks for your attention.
Okay, thank you very much, Sudipta, for your lecture, seminar. Do we have any questions?